In this video, we would consider an example on how to convert complex numbers in the algebraic form into the polar form. Now, this in this case is a power multiplication such that, of course, you have a complex number raised to another complex number in this case, such that it's not so easy to expand binomially as the case is. Now, in order to do this, the very first thing is we will break down different parts of the complex number into simpler workable parts before we then proceed. Now, first and foremost, we will consider the fact that if we consider the inside of this power such that we consider z to be 1 plus I, which is the inside, which is of course a complex number, we can convert this into the exponential form. Now, if we convert this to exponential form, what exactly does that do for us? What it does for us is that first and foremost, because of this, we would be able to rewrite the inside as a power, because the exponential form is of course written as a power or as an indices. In that case, it will be easy to apply the law of indices with the outside power and bring them all together. Now, to do this, of course, for z, we would need to find the radius, which is the modulus, that is square root of x squared plus y squared. That's where we compare, of course, with z being equal to x plus iy. Now, we would also have that the argument would be the arctan of y over x. Now, from here, the radius is of course given to us as 1 squared plus 1 squared, that is the square root of 2. We are just going to leave it in its full form as the case is, and then the argument is going to give us the arctan of 1, and of course the arctan of 1 is indeed going to give us pi over 4. Now, we know it's pi over 4 because 1 plus I represents a value in the first quadrant. Remember, when dealing with complex numbers, it is very, very important to consider the signs of the complex number so that you are very, very sure where the complex number is directed towards, and that would affect what the argument is, as the case is. Now, based off this, we can say that we can write z, which was originally 1 plus I, we can write it as root 2 e raised to the power of I pi over 4. That's how we would write it in the exponential form. Thus, it would follow immediately that 1 plus I raised to the power of iy would now be equal to root 2 e raised to the power of I pi over 4 raised to the power of iy. Now we are getting somewhere. By law of indices, this would split into root 2 raised to the power of iy multiplied by e raised to the power of I pi over 4 raised to the power of iy. Now, by law of indices, this power can combine. I times I will give us I squared, which is minus 1. So in this case, we are going to have root 2 raised to the power of iy multiplied by e raised to the power of minus pi over 4y. And that's our combined form. Now, we have this. We can, of course, simplify the left-hand side. So we do not have to always write something so complicated. That would mean that w would be equal to, now you have root 2 raised to the power of iy. You could decide to bring out the square root, have that as 2 raised to the power of iy over 2, because the square root of 2 is the same thing as 2 raised to the power 1 over 2. And then, of course, this would multiply e raised to the power of minus pi over 4y, or pi y over 4 as the case is. Now, from this notation, remember the goal is to write it in polar form, which means we still have to combine this and work with it. Now, it's in power forms, right? And the easiest way to do with power forms, especially the ones that contain the exponential, is to take the natural logarithm of all sides, in this case of both sides. So if we take the natural log of both sides, we would have immediately that ln w would be equal to ln 2 iy over 2 e raised to the power of minus pi y over 4, right? Now, by law of logarithm, when you have the number inside being a product, it could break such that you would have this to imply that ln w would be equal to ln 2 is the power of iy over 2 plus ln e is the power of minus pi y over 4. Now, this is very, very interesting because by law of logarithm, yet again, the power slips to the left. I have iy over 2 ln 2 minus, of course, because this is minus pi, y over 4 ln e. But of course, ln is log to the base of e. So ln e gives you 1. So if that's the case, it means that this, which is ln w here, would have that ln w would simply give us iy over 2 ln 2 minus pi y over 4. Now, if this is the case, what happens is we can revert the process by taking the exponential function of all sides, in this case of both sides. So if we take e ln w, that will give us w. We'll come back to that in a minute. And then we have e raised to the power of iy over 2 ln 2 minus pi y over 4. So here we're going to have w equals e raised to the power of iy over 2 ln 2, right? By law of indices, this will now be divided by e raised to the power of pi y over 4, right? Now, you could write it like this, or you could just simply apply another law of indices where you split this based off the multiplication, and you could write it as instead e raised to the power minus pi y over 4, which is much more interesting, multiplied by e raised to the power of iy over 2 ln 2. Now, because the I is here, it looks as though y over 2 ln 2 is in fact the argument of this complex number, which means if you were to convert that in its polar form, you'd have this to be e raised to the power minus pi y over 4 multiplied by the cosine of y over 2 ln 2 plus I sine y over 2 ln 2. And that completes the process. So we've been able to work our way from the exponential function into the polar form. So you can of course say that for this complex number, this is its radius, and then this is its argument, right? So this is your r, and this is your theta. Very, very unique question. So this question showcases the potential that exists when it comes to expressing polar multiplications or power multiplications. This time around, not a complex number raised to the power of 3 or 4 or 5, which you can just simply apply the De Moivre's theorem to. But this time around, raised to a complex number in itself. In this case, you could work your way around this so as to get the complex number it is attached to. And of course, from here, you could find out the values of this in its polar form, and you know that this is, of course, a complex number in this case because you have the real part, and then you have, when you expand, the imaginary part coming out in clear terms. So it qualifies as a genuine complex number. So this solves the question. I hope you were able to get all the steps for this. As always, make sure to like, share, and subscribe, and join us for our next